So today we're going to continue with our discussion of liquids and solids, and we're going to talk about molecular and ionic solids. So last time we talked about atomic solids, mainly network solids, and now we're going to cover the other two main types. Okay, so molecular solids basically have molecules at the lattice points instead of atoms. And so ice is an example of a molecular solid because we have H2O molecules at each of those lattice points. And so an example of that is down here. Ice forms this very crystalline structure. Dry ice would have solid CO2 at each of the lattice points, and so here is an example of that type of molecular solid. Some other forms would be sulfur. Sulfur exists as S8, so again that's molecule, and phosphorus, which exists as P4. All these molecular solids have strong intramolecular forces, so the forces between the atoms in the compound are very strong, and tend to have weak intermolecular forces, so the bonds between the atoms, or molecules rather, are somewhat weaker. The forces among the molecules depend on the nature of the molecules. So for example, most of them don't have a dipole moment. If we think about CO2, it is a nonpolar molecule, so no dipole moment, so those intermolecular forces are going to be relatively weak. But because this is a molecular solid and we have a ton of CO2 molecules that are forming this solid, as the molecule gets bigger, London dispersion forces will get more prevalent because London dispersion increases as the size of the molecule increases. If, like water, or ice rather, they do have a dipole moment, then intermolecular forces are usually going to be greater. So for example, hydrogen bonding, which is occurring in the water molecules, or the ice solid. And the other form that we're going to talk about today are ionic solids. So ionic solids are made out of charged ions. They are stable, they have high melting points, and that's because the substances are held together by really strong attractions between the cation and the anion. And these structures tend to form, we talked earlier about how the atoms will go together. So these are closest packing. They try to take up all that space. And so what happens is the large ions, usually the anions, because they contain more electrons, are packed in an HCP or a CCP arrangement. And remember, we talked about those, the hexagonal or the cubic closest packed arrangement earlier in the unit. And then those small cations will fit in the spaces left by the larger anions. And basically, this arrangement maximizes the attraction between the cation and the anion and minimizes the repulsion between, let's say, two cations or two anions. Okay, there are basically three types of spaces for those cations to go. Okay, the first is trigonal, and this is where we have three spheres or three atoms in the same layer. The holes between these are too small for binary ionic compounds. Okay, the other example is tetrahedral. This is where the sphere sits in a dimple of three spheres on an adjacent layer. So we have, three on the bottom layer, 1, 2, 3, and then our fourth one's going to fit in the center on the top. And the last one is octahedral. This is between two sets of three spheres in adjoining layers. And basically, the size of the cation and the anion is going to determine whether it takes on a tetrahedral or an octahedral hole shape, basically. Because trigonal, it's too small for binary ionic compounds. Okay, so here's the examples. So here we have basically it fitting into this space, and that's just too small for binary. Here we've got our two layers. Okay, and so it's going to fit in the space between the bottom orange atom, which is about right here, and then these three yellow atoms. So it's fitting here. We've got more space. And then the octahedral hole, okay, we've got a space between our yellow ones and also a space between the three orange ones if you looked like over here and took this hole and moved it right underneath this one. So again, we've got a little more space than trigonal, and so that's how binary ionic compounds are going to be structured. Okay, so let's take that example and determine the number of determine the number of ions in a unit cell. So we want to determine the net number of sodium and chlorine ions in a sodium chloride unit cell. Now, because NaCl is an ionic solid, it's going to be cubic closest packed, which means it's face-centered cubic. Okay, we've talked about these shapes beforehand. So let's take a look at the chlorine first. We know on each face of the cube we have half of an atom. So since there are 1, 2, 3, 4, 5, 6 faces, that's 3 atoms. And then in each corner we have an eighth of an ion. And so we've got 8 corners, and that makes 1 more, so we have 4 chlorine ions. And now let's look at the sodium. So on each face we have 1, 2, 3, 4, and then we'll want to make sure that we don't double count it. Basically, if you count all of these up, you're going to also get 4 sodium ions. And so since we have 4 chlorine ions to 4 sodium ions, that means our ratio is 1 to 1, which justifies the compound being NaCl, being in that 1 to 1 ratio. Okay, last example. So, based on what we have discussed, we've talked about atomic solids, molecular solids, and ionic solids. Can classify each of these as the type of solid that it forms. So we have a gold solid, carbon dioxide solid, lithium fluoride solid, and a krypton solid. So go ahead and pause the video. Think about these 3 general types of solids that we've discussed and see if you can assign each example its type of solid. Okay, so go ahead and pause and do that now. Okay, hopefully that is what you have done. And so here are your answers. So gold is atomic. It's also got a little bit of a metal characteristic. Carbon dioxide is going to be a molecular solid. Lithium fluoride, because those are cations and anions, is going to be an ionic solid. And krypton is again going to be an atomic solid. Okay, so hopefully this has helped cover the 3 main types of solids.